this session I show you how to visualize the components of the stress tensor, all the stresses you find in the tensor. As an example, I used a C profile. It's 1 meter length. I put 1000 kilo of charge, so 10,000 Newton on this side in the shear center. Where did I get the information of the shear center? If you look at this table, I use this UAP profile. I used the size 100, and there you find the information where this shear center is. It's given through the E and the RC value. These two values you find on this side, and you just have to subtract one from the other. So I get here the information that the shear center is here 60.8 millimeter on the other side, on distance from here. So that's what I modeled here, just this shear center point. I calculated, I charge now the results. I see that I've used hex elements for as finite elements. If I look on the displacement, I see I have not visible torsion. So I go to the stresses. As first I look at the stress von Mises. I'm not interested to see the connector elements. I'm not at all interested to see the elements, so I only look at the model. Then I make combination at the nodes. You see the max here, 384, goes down a little bit. It's almost nothing visible, but it's quite that. Then I change. That's okay. I go that I have no deformation visible, and now I just go and make a cut plane, and I make the cut on both sides. So you see now I've the information just on a cutting plane. I can put the different levels. I will show the largest and the smallest, more comprehensible. If I go to the X direction, and I can also look at the shear, or have the shear information. You're used to see that in a better way. I can show that in not contour, that I choose tensor. I apply, and you see a lot of vectors. I can go down, change to normal components, apply. Now I have the X, Y direction. I prefer the solid visibility, and I can put here also the size. It's a little too small, so 10 millimeters. That's not so bad. If I look on this, I see really these vectors, and I can here, see that normal components, it's going from about here compression 177 megapascals to traction 178 megapascal. That's about the thing I wanted to show you. A little bit larger, and you have the image like you find it in a lot of illustration, compression, traction. That's it. I can change to shear component and look at the shear, and you see this XY shear. It's not really good comprehensive, but up there it's the shear in XY direction. We look at the ZX direction, and you see a lot of shear in this direction, a little too much of vectors, so you change the size, it's a little bit better visible like this. Shear is going, you have all the time two components of the shear, X, Z and ZX, set in this cutting plane. I can also visualize the max shear, and you see the position of this max shear. Also, max shear has this different planes. That's the plane of the max shear, and you see here the values which are here for shear at which point. You can also look at the principal components. I look at the max principal, and I see where I have traction, and with min principle I see where it is compression. I have both together now. I can also go and say I looked at on the whole volume, but as you see it's more or less invisible, so I really think it's better to put it on a cutting plane both sides. That's the thing, how to understand these different components. You find this also here. Here I changed tensor. I can also put spheres. What I have visualized are the min principle, max principle, the max shear. Can change also to isosurfaces. That's not really interesting if you see that on that its cubes are more or less the same. So stay with tensor, and it's really an interesting picture here. That's now tensor part, but max principle, min principle, shear, and as I said, x direction and y direction we find more or less nothing, and we have no direction there. Z more or less also nothing, but you have something in the x, y and yx, and you have a little bit more on the z, x, z direction. I just close this cutting plane and I go back on ISO surfaces of von Mises, and you see all the areas with the same stress. You can do that also with the surfaces, with the areas of the largest stress max principle or min principle, set in this area where you have to put the layer on a carbon fiber, and here you see the shear that's more or less at the same area here, x direction. Okay, that's all what I wanted to show to you. I put it on the Moodle, the file with torsion, no torsion. I've presented you this with no torsion, so use that, and then as a second you try the same thing and look at the different stress tensor parts, stress components in the C profile with torsion. That's all.